Hi, everyone. Welcome to the Simons Institute. I'm Avishai Tal. I'm an assistant professor at UC Berkeley. For those of you who are not familiar with the Simons Institute, we are the leading venue for collaborative research in theoretical computer science. Established in 2012, the Institute brings together the world's leading researchers in theoretical computer science and related fields. I'd like to welcome you to the workshop on logic and algebra for query evaluations. This is part of the program on logic and algorithms for database theory and AI. I'd like to thank the organizers of the workshop for putting together a great program. There are Sudeepa Roy, Wolfgang Gaderbauer, Dan Succio, and Val Tannen. So let me mention a few things about logistics before we start. So food will be provided before the first talk of each day and during the breaks. Lunch is on your own, but there are many good options around. We ask that you please leave the food and beverages outside this auditorium. And if you're looking for storage, there are lockers on the other side of this floor. Finally, all talks will be live streamed and available later on the website. And our videographer, Omid Farr, will help speaker get set up before the talk. Finally, I'd like to give special thanks to the events team, Ashley, Frida, and Lyra, for managing all the logistics for this week's event. And now I will hand things over to Sudeepa, to Dan. To Dan, who will say a few more words. Okay.
Okay, thanks, Avishai. And I'd like to thank all the local organizers for enabling this workshop. So our topic this week is extending queries and logic with numerical computations, and more generally with computations over abstract semirings. So this includes new semantics for logic, extensions of query languages with numerical computations, and lots of quite exciting and surprising applications that all seem to need this extension of logic with numerical computations. So our goal was not just to bring people together, which is always a good goal of the workshop, but we also think that there are several apparently divergent applications that can actually benefit from a common framework. And this is our goal, to discuss this common framework that can benefit multiple applications. So the talks are scheduled over 5 days. We have time for discussions every day and for discussing open problems. Think about open problems and questions you might have. I should also mention that some of our speakers, they really wanted to come, but they had to cancel at the last minute because of events in Israel. So they will give talks online. A small number of talks will be online. Okay, on this note, I would like to introduce the first speaker, Erich Graedel, who will talk about new semantics for logic based on semirings. So Erich, please take it away.
Thank you very much for the invitation. I would like to talk about semiring semantics, and this has its origins in semiring provenance that started with the seminal work by Green, Karvounarakis, and Tannen a long time ago, 2007. And the basic idea of this approach is to annotate the facts of a database by values in some commutative semiring, and to propagate these annotations through a query, keeping track of whether you use information jointly or alternatively. So the idea is that the plus operation of the semiring interprets the alternative use of information, as for instance in disjunctions and existential quantifiers, whereas multiplication interprets the joint use of information, conjunctions, universal quantifiers. So the zero element of the semiring just stands for false, and all other elements provide some annotation of true facts. When we take an information for granted, do not track it any further, we interpret it usually by the one element of the semiring. Now, the idea is that with this approach you can get detailed insight about which combinations of atomic facts are responsible for the truth of a statement, and from this you can derive additional information beyond the truth, just cost, confidence scores, access level, number of successful evaluation strategies, and so on. So, some words about semiring. Well, you know, of course, what a semiring is, but let us go through some examples of those semirings that are relevant for this approach. Of course, the simplest semiring is a Boolean semiring, the Boolean truth value, so in a sense we have always done semiring semantics. Another important semiring is a semiring of natural numbers, which is important in back semantics of databases. Here it's mostly used for counting objects, counting proof, counting evaluation strategies, and so on. Then a less well-known example is a tropical semiring over the non-negative reals together with infinity, where the operations are min and plus. So the min stands for the alternative use of information, plus stands for the joint use information. And this semiring is used in many fields in computer science for cost computations. There is another semiring that is in fact isomorphic to the tropical semiring, the Viterbi semiring over the real interval between 0 and 1, where the operations are max and times. And this is a semiring that can be used, for instance, for confidence scores, although I find this interpretation much less convincing than the one of the tropical semiring for costs. Then there is a large class of min-max semirings. So they are just induced by some total order, and then you take max and min as the two semiring operations. 0 and 1 are the least and largest elements. So one example is when you take the real interval between 0 and 1. This is often called the fuzzy semiring. But there are also finite min-max semirings, and one particular example is so-called security or access control semiring, where we have an order of access levels, like inaccessible, top secret, secret, confidential, and public. And you will use the semiring to reason about the access levels to information that are necessary to evaluate a query. And a more general class are the lattice semirings, where are not induced by a total order, but by a partial order. So it takes the inf and sup as semiring operations. And then there is, from the field of many-valid logic, we can also take the Vukašević semiring, which can be seen as an alternative semiring to reason about confidence score, or about degrees of truth, where the addition operation is against the max, but the multiplication is something a bit more complicated. And this semiring is in fact isomorphic to what I call the semiring of doubt, the reason about doubt, and where the plus operation is minimization, and the interpretation of the joint use of information is a truncated variant of plus. So your doubt increases when you have used information jointly, but it's cut at 1, the maximal doubt. So least confidence. Now, you saw that I was not talking about rings. Rings are, of course, also semirings, but we are not interested in rings. We are interested in semirings that are partially ordered by addition. So you have this order here, A is smaller than B if A plus C equals B for some C. And this is always reflexive and transitive, but it's not always antisymmetric. So we require it to be antisymmetric, so this excludes rings. Right? We're interested in partially, naturally ordered semirings. So these semirings can all be called sort of application semirings. They give you some particular information about a logical statement or a query, but they do not answer the fundamental question that I have mentioned at the beginning. So which combination of the atomic facts are responsible for the truth of a statement? Right? And for these, we use another kind of semiring, so called provenance semirings, and they are, in general, semirings of polynomials. So take a set of indeterminates, and these indeterminates are used to label the facts that we want to track. So we associate it with an atomic fact, an indeterminate and then considers the semiring of multivariate polynomials over these indeterminates with coefficients in the natural numbers. So this, in fact, is algebraically, this is a commutative semiring that is freely generated by this set of indeterminates. And they have an important universal property which justifies to say that this is the most general semiring for this purpose, namely any function from these indeterminates into a particular semiring extends uniquely to a homomorphism from this polynomial semiring into the semiring S, right? And we can just think of the homomorphism as the evaluation of the given polynomial inside that semiring. And this semiring is a quite complicated semiring. So it gives a lot of information, that this information is also a bit difficult to compute. So there are alternatives. The alternatives are to use some simpler polynomial semiring where you lose information with the hope that this information is then easier to compute. And there are several possible operations to simplify from this general polynomial semiring. So one is that you drop the coefficients, right? So in a sense you are not interested in so how many times you can achieve something with the same atomic facts, but it just suffices whether you can do it or whether you cannot do it, so it just drops the coefficients in the polynomial. An alternative simplification is to drop the exponents, which corresponds to, I'm not interested how often I use a particular atomic fact, I'm just interested in whether I use it or whether I don't use it, right? And so we just have monomials that are linear in each variables. Or you can do both, right? You can both drop the coefficient and the exponent, and then you get a sum of monomials that are linear in each argument, and well, you don't have any coefficients anymore. Besides these dropping coefficients or dropping exponents, there is another operation that is important in this context, and this is absorption. Absorption corresponds to the observation that if you have a logical statement, psi or psi and phi, then you can simplify this and just take psi. Right? So the psi absorbs the conjunction, and this is what we do also here. So we absorb here, and this means that xy absorbs x square y, because a monomial always absorbs those monomials that have larger exponents. Right? So you simplify this further, right? And you can apply this to this semiring with Boolean coefficients, or you can apply it to this semiring here, so so-called the y semiring. And so if you do both operations, you end up with just irredundant, so positive Boolean operations, so irredundant disjunctive normal forms, right? So, and for many applications, this semiring is good enough to compute what you want, right? And it's, of course, it's easier to handle, right? So this is as a general picture of these polynomial semirings. So we will see in a more detailed way what you can do with these polynomials in a somewhat more general setting that I want to introduce now, right? So this approach of semiring provenance, mapping logical statements to semiring and deriving information from that, has been pursued for a quite long time in database theory and has been quite successful, right? But for a long time, it has essentially been confined to positive query languages, right? Like positive relational algebra, unions of conjunctive queries, to a lesser extent also data log. Right? For data log, you need further conditions on the semiring, and I will come to that later, right? But all these query languages are positive. They do not involve negative information. They have no negation operator. And there have been approaches particularly to deal with difference of relations, so-called monosemirings and so on. But an evaluation of Valtan, I think back in 1915 or 16, was that all these approaches are in some sense unsatisfactory and diverge in many directions, so the state of affairs has been considered unsatisfactory, right? And also the absence of an adequate treatment of negation has been an obstacle to extend this approach to other fields of logic and computer science, right? One can argue that in databases, you can get quite far just with positive information. There are limitations, of course, but still you can get a long way. But I don't think this is true in other fields, right? Like in verification or so. I mean, you just need also negative information. And so to make a provenance or a semiring approach successful also in other fields, you need a treatment of negation, right? And the problem is that negation is incompatible with the algebraic semiring operation, right? So, and in fact, in many scenarios, this is not just in provenance, it's also, for instance, in team semantics, right? There are people who know about that here, right? Negation is not really a logical operation. And this means, if you have a formula phi, right? And you have evaluated, for instance, in a semiring. This doesn't give you information what the value of the negation of phi is. That you cannot derive the meaning of the negation of phi just from the meaning of phi. You need to have a closer look at the syntax of phi in order to do that. Right? I mean, it's clear if you interpret false as 0 and every other element of the semiring as true, then the negation of a false statement, you don't know which degree of true is there, right? You have to really look at the formula in a closer way. So what we did has been largely triggered by a decision of the staff of the Simons Institute in the program of 2016. Namely, they put Val and me into the same office, right? Previously we knew of each other, but we hadn't met. So we talked about what we're doing, and Val told about this problem of providing semiring semantics or a semiring provenance for full first-order logic with negation, right? And so we talked about this, and what I had worked at that time mainly on were infinite games, game theory, model checking games, right? And in model checking games, you also have a problem with negation, right? Because negation in an evaluation game corresponds to a role switch of the player. What previously has been the verifier becomes the falsifier and vice versa. And you want to avoid role switches during playing of the game. It's very difficult to reason about strategies if in the middle of the game the player changed their roles, right? So what was one pushes the negation to the atom, one transforms this to negation normal form. So the question was, does this also work reasonably well in semiring semantics, right? It's not obvious because you have these polynomials, right? And you have to deal with that. So what we came up with was a new approach to deal with negation. Well, first, negation is handled via transformation to negation normal form. This also means that we need new semirings of polynomials, right? That have two kinds of indeterminates, the positive one and the negative one. But of course, there must be a reasonable relationship between a positive fact and its associated negative fact, which means that you have to move to some quotient semiring to deal with that. And it turns out that this provenance for logic is intimately connected to a provenance analysis of game, and the negation is related to the antagonism between the two players. And in fact, provenance for game is of independent interest and provides interesting insights into strategies that you have in a game far beyond the question who wins the game. Yet we will see this later. So this also leads to new kinds of applications, so repairs, missing query answers, but I'm not really talking about that in this talk. So, well, negation normal form, what does it mean? So it means negation is applied to atomic formulae only, so the formula negation normal form are just obtained from the atomic facts, their negation via positive operations, disjunction, conjunctions, and quantifiers. And of course, an arbitrary formula can efficiently be translated to the negation normal form by a very simple process using the De Morgan inequalities and the duality of quantifiers, right? So once you have it in negation normal form, evaluation is a positive process depending on positive and negative atomic facts. So this leads now to the notion of a semiring interpretation. So fix a commutative semiring, fix a finite universe and a finite relational vocabulary. Then you have the literals over that universe and that vocabulary. They're all fully instantiated atoms and negated atoms. And a semiring interpretation for a semiring S is just a function mapping these literals to values in the semiring. Right? This can easily extend it by evaluating equalities and inequalities just by their truth value 0 and 1, which means we take the universe for granted. We do not track equalities and inequalities, right? They are just accepted as they are. Now, we call such a semiring interpretation model defining if it has a certain consistency properties on the atoms and their negations, right? So we say it's model defining if for each such atom precisely one of the values of the atom and its negation is 0. And if we have this condition, then such a semiring interpretation specifies a unique structure, namely those structures where all the literals are true that have a positive value, right? But we'll see not only these interpretations are interesting, it is also interesting to consider semiring interpretations that are not model defining and that do not define a unique structure but a class of structures. So once we have this, we immediately get a semiring semantic for all first order sentences. Right? So we extend this interpretation to evaluation of fully instantiated first order sentence. So we denote this in this way. This is a semiring value, the semiring valuation of the sentence phi, right? And this just follows the intuition that we have. Disjunction corresponds to addition, conjunction corresponds to multiplication, and of course for the quantifier, we just take the sum or products over the elements of the universe, right? So we assume here that the universe is finite, right? But we can also do it with infinite universes, provided we have semirings where we have reasonable infinitary sum and product operations. This in fact works in most of the semirings that we had, but it does not work, for instance, in the natural numbers. Right? Natural numbers, you cannot have an infinite addition without going outside the natural numbers. So you have to extend the semiring by infinity elements to make this work. Right? So in general, the approach works also for infinite universes, but you have to be a bit careful which semirings you use. So I thought we also need new polynomial semirings if we have this. Right? So the idea is now to annotate atoms by indeterminates in a set X and negated atoms in a other set X bar with a bijection that relates every indeterminate with a partner in the other set, right? So that you have, I mean, you want to label a specific atom by a positive indeterminate and its negation by one, so with the association, right? And the semiring you consider is a quotient semiring of the polynomial semiring over this full set of indeterminates, right? So the quotient semiring with respect to the congruence that is generated by the equations x and x times x bar is 0, right? So this equation, of course, means that a literal and its negation cannot be true at the same time, right? Their product is 0, right? So this quotient semiring corresponds just to polynomials with the property that no monomial may contain complementary token, right? These are all deleted because they evaluate to 0, right? And of course, for the semiring n to the x, we had a universal property, right? Do we have also universal property in this setting? And the answer is yes, we have, but we have to assume a stronger condition, right? So any map from the indeterminates into a semiring subject to the condition that the value of x times the value of x bar is 0, again uniquely extend to a semiring homomorphism from this into S. So what can we do with it? So I think in databases one often argues about proof trees. Is this? So a proof tree, and what is a proof tree? A proof tree is really an evaluation tree that gives a positive value. So it gives you a process that whenever you have, say, a disjunction, you just choose one of the disjuncts. If you have an existential quantifier, you choose one of the instantiations of that quantifier. But if you have a conjunction or a universal quantifier, you have to keep in your tree all the possible children of that, right? So it is a strategy, in a sense, how to evaluate the given sentence, right? And so it's really the same as a strategy in an associated evaluation game. So if we have such an evaluation trees, we consider for each literal alpha the number of leaves of the tree that are labeled by that literal alpha, right? And the valuation of the tree is just the product over all values of literals that occur in the tree, right? So we can say the product over all literals, the value of the literal taken as often as it occurs as a leaf in the tree. Now what is a proof tree? A proof tree is just an evaluation tree that does not evaluate to 0. Right? And there is a general theorem that tells you that for every semiring interpretation, in particular semiring and every first order sentence, the valuation of the statement is the sum of the valuation of its truth trees. Right? And when we now look at this, what it tells us in this semiring for dual indeterminate polynomials, we get the following, right? So we consider a semiring interpretation into that semiring of dual indeterminate polynomials. We assume it is model defining, that is, if you map a literal to something non-zero, the opposing literal has to be mapped to 0 and vice versa, right? And we assume that each literal is either tracked, that is, it is mapped to an indeterminate, or it is not tracked, that is mapped to a truth value. What does the previous theorem then tell us, right? Or what does the provenance polynomial of that sentence tell us about the model checking problem whether C is true in the structure that is defined here? Right? It tells us the following. Right? Recall this is what we had. Right? The value of the sentence is the sum of the valuations of its proof trees. But now the valuations of proof trees are monomials of that form. Right? So it tells us that this provenance polynomial is a sum of monomials of the form, well, m is a natural number, and these are the indeterminates, and these are the exponents. So each such monomial tells us there are precisely m proof trees which use amongst the trapped literals only those that are labeled by x1, xk, and more precisely, it uses the literal labeled by xi, or literals labeled by xi, precisely as many times as the exponent tells you. Right? The untracked literals, they may be used arbitrarily. Right? So it gives you a precise description of the proof trees that you have for evaluating your statement. So it answers that question, which combination of basic facts gives the truth of the statement, and in fact in a very precise way. Right? It tells you all about the evaluation strategies and what literals they used. So in particular, if you evaluate atomic facts just by 0 and 1, then it will just count the number of proof trees that you have. Right? So, and of course, in particular, a statement is true in the structure defined by this model-defining interpretation, if and only if the polynomial is not a 0 polynomial. So, yes?
Is a proof tree of psi the negation normal form of psi and pi, or what?
Psi is a formula that we may assume to be a negation normal form. pi is the semi-ring interpretation. That's the interpretation that in this case defines a particular structure but gives much more information about this structure. Right? Yes, okay.
Am I right that for this interpretation to be model defining, you cannot map a literal to x and the negation to x bar? Is that correct? So one of them has to be 0, right?
That's to 0. But let's look at the next slide. So you have, as I said, model defining interpretations are not the only interesting interpretation, right? So they are a class of what we call model compatible interpretations, right? So an interpretation is model compatible if for every atom it either maps the atom and its negation to complementary indeterminates, or it maps them to 0 and 1. So it's just to their truth values, right? So a model compatible interpretation is consistent with at least one structure on the universe, but in general with a larger set of structures. So we have those literals that are evaluated to 1. So they must be true in all models of the interpretation. And you have those literals that are mapped to indeterminates that can be true in some models. Right? And if we now have evaluation of a first order sentence with respect to such an interpretation, then this provenance polynomials describes those proof trees whose leaves are in must or may, right? So it must be true or they may be true, right? So every monomial corresponds to one proof tree and gives precise information about the literals on which this proof tree depends, right? So it gives a complete description of all models of the sentence that are compatible with the given interpretation, right? So it's a more general setting of that. Okay, so this is basically what we did when we met some years ago at the Simons Institute to develop this theory. Now, meanwhile, we have become a bit more ambitious. So what's the goal really is to develop semi-ring semantics as a general theory that does not just apply to first-order logic, does not just apply in this database setting, but as a general logical theory, right? And there are a number of research programs that are associated with that, some of which I want to talk about the second part of my talk now. And well, one program is to push this beyond first-order logic. Right? In fact, we want to have a semi-ring semantics as a general approach dealing with any kind of logic. Right? For some logics, this is straightforward, completely trivial, but for others, it's not straightforward, and particularly, it's not straightforward for logic with fixed point. I mean, I come from finite model theory and infinite games, so I'm mostly interested in these logics, right? But of course, there are many logics that go beyond first-order logic by some kind of recursion or unbounded iteration mechanism, right? All these logics in verification, for instance. So we want semi-ring semantics be useful for all that. Then we want to analyze game, right? So these basic, and since first-order semi-ring valuations, you can view them as a strategy analysis of the model checking games for first-order logic, and these are just acyclic reachability games, right? Games on trees, basically, or games on DAGs, right? But there is a generalization, which we'll talk about later, with omega continuous semi-rings, where you have required that whenever you have an ascending chain, it has converged to supremum that is compatible with the semi-ring operations. And these are the semi-ring that are that work for things like data log or so. And in the games theoretic setting, this works for reachability games that may possibly have cycles, right? But it does not extend to games with more complicated winning conditions, such as Büchi games, parity games, or just as games with incomplete information, right? So the question is, can we also provide a semi-ring-based strategy analysis for such games?
What do you mean by strategy analysis?
You will see a result that tells you what information about all the available strategies in some class for a given player. And the third is, well, once we have extended this to many logics, the question is, do the usual theorems and tools that we have in logic also work in semiring semantics? And this is not trivial, right? I mean, going to semiring semantics may destroy many things we know in logic. So to what extent do classical results of logic generalize to semiring semantics? And how does this depend on the properties of the semiring, right? In most cases, it works for some semirings and it does not work for others. Right? So let me talk about these three. There are, of course, many other points, right? So it's one should develop a proof theory for this as well, and so on, right? But these are things where we already have some results. So fixed point logic, right? So semiring semantics has meanwhile been extended to many other logics, and the most interesting challenges are when you have fixed points. Right? And of course, for a particular fixed point logic, namely data log, this has been done a long time ago. Already in the first paper by Green, Karunavakis, and Tannen, it has been done for data log, and there has been a more detailed analysis some years later that also gave a circuit evaluation for data log with semirings. Right? And this is based on omega continuous semiring. That is a semiring, basically it's a semiring where least fixed points exist. Right? So universal ones are no longer semirings of polynomials. They are semiring of formal power series, which just means potentially infinite sums of monomials. Right? And with dual indeterminates, which we can add not just to polynomial semirings, but also to semirings of formal power series, this pushes this somewhat further. It provides a semiring semantics for semi-positive data log, that is data log where the input predicates can also be negated, but not the computed predicates. And for what we call a positive fragment of least fixed point logic, that is a fragment where you can build fixed point, but you can only build least fixed point and not greatest fixed point. You cannot negate least fixed point, right? So, however, in the general fixed point logics and also in the model mu calculus, you may have arbitrary interleavings between least and greatest fixed points, or between negation and least fixed point. And the omega continuous semirings are not adequate for these, right? You can't do it with omega continuous semirings. So the question is, what are the algebraic conditions that are required when you have these larger settings, right? You have to impose some additional conditions on your semiring. And there are basically two conditions. One is full continuity. That's quite obvious observation. You don't have just ascending chains have to be a primum, but also descending chains need to have an infimum. And this must be compatible with the semiring operations, right? And this condition already suffices to get a well-defined semantics for both least and greatest fixed point. But it is not yet really a meaningful semantic in the sense that it tells you something relevant about the sentence, maybe pathological semantics. To make it really work, we need the additional condition that has also been well known before and used in many settings, that is that the semirings should be absorptive. Now this is a law of absorption that we already had in this simplification of the polynomial semirings, right? So it says that a product AB is absorbed by A for any AB, right? But the important consequence of this, or in fact an equivalent characterization of this in naturally ordered semiring, is that multiplication is decreasing, right? And this should be the case, right? When you have, because it means, for instance, that the conjunction has, in sense, a smaller value than the conjuncts, right? It should, psi and phi should be less true than psi, right? And this is true in all these absorptive semirings, but it's of course not true in the semiring of natural numbers, where multiplication increases. So, in a sense, we throw away the semiring of natural numbers when we impose this, right? And so, what we analyze this, and it shows that indeed absorptive fully chained continuous semiring, fully continuous semiring, I should have written. Each monotone function has a least fixed point and a greatest fixed point, and this gives a meaningful semantic for least fixed point logic.
Erich, but can you explain why do you need absorption? Because Nastarsky will give you that if the functions are monotone, there is always a least and a greatest fixed point. So why
yes, but it will not be, in a sense, the dualities between least and greatest fixed points will no longer survive.
Which duality? Sorry, I don't.
That's a negation of a least. So you have. I mean, you just. I mean, you can define a semantic, but it will not give you very reasonable information about the formula. And so the question is, do there such semirings exist, right? And they do. In fact, most of these application semirings, like the tropical semiring, Viterbi semiring, Max semiring, lattice semiring, Lukasiewicz semiring, they all have these properties. But semirings that do not have these properties are these general semirings, like semirings of polynomials over the natural numbers, semirings of formal power series, and so on. So the question is, is there also a notion of the most general semirings for fixed point logic in this setting? And there is, and these are the semiring of generalized absorptive polynomials. What are they? The polynomials have this form. So what are the features? You don't have coefficients, right? So the natural numbers are thrown away. They cause problems, so we just have Boolean coefficients. The exponents on the other side may also be infinite. So you have an infinity as a potential exponent. And you have absorption among monomials. So if you have a monomial and another one that has for each variable a larger exponent, then the one with larger exponents is absorbed, right? And a consequence of this is that there is no longer a different notion between polynomials and formal power series, because you can say such a polynomial is an anti-chain of monomials with respect to the notion of absorption. And these anti-chains are always finite. So every formal power series is, in fact, already a polynomial, right? So you don't need this distinction, which simplifies things a lot. Of course, you can do as well. Again, when we have this, we can add the dual indeterminates, which we need when we want to interpret also negative fact. And these have universality properties that indeed make them the right general semirings for fixed point logic. Yes?
So if you have the dual indeterminates, s infinity x, x1, then only either x can be present or x bar.
In each monomial, yes. But in different monomials, it's okay. Yeah. But in the same monomial, if you have both, they will cancel out.
Okay. But in a different
Yeah. Yes, okay.
If I care about this fixed point logic on finite structures, then we have the Ingerman complementation theorem. One application of this fixed point suffices. There is a price. We have to increase the arity. Why isn't this satisfactory, in which case you only use omega continuous semirings to give semantics? I realize it doesn't work for modal logic because of the increase in arity. But what about this fixed point logic?
Well, I mean, this increase of the arity, it's a very complicated process, right? I mean, you need a stage comparison theorem that...
It's expressible in this fixed point logic.
Expressible, yes, but at a price, right? And
what is the problem? We're looking here at the philosophy behind what semirings do I need to give semiring semantics to my logic. And of course, it's very nice to go to what you've done with a fully continuous absorption, but to me, if I just want to stick with omega continuous,
you can do it, but I mean, it's when you do this transformation, it's not clear what you lose, right? I mean, this is a Boolean transformation, right? And it's not clear that it preserves the semiring properties.
Has anyone looked at if it preserves?
I don't think so. Do you know that?
I mean, it does not preserve the semantics. It can't, because if you have greatest fixed points, then we can express something like x to the infinity, and we cannot get this from a least fixed point. I mean...
Okay, we should take it offline. I would like to see this
also, I think the transformation will probably change the way the formula works, and so it will change the provenance information that we would get.
Thank you.
Yeah.
So, let me see a look at an area where this can be put to use, right? So in fact, with these fully continuous and absorptive semiring, we can provide a strategy analysis for more complicated games than reachability, in particular for Büchi games. Right? And the core of such analysis are what we call sum of strategies theorem. Right? So to have such a sum of strategies theorem, we need some ingredients. Right? So we need an appropriate semiring that is based on a labeling of moves by indeterminates. We need evaluation of game positions. No? Often we do this in the following way, right? So we take a fixed point formula that tells you this position is a winning position, it belongs to the winning region, and we look at its semiring valuation, right? And we have an appropriate class of strategies. Usually we cannot take all strategies, but we can take, usually we also don't take just the positional strategies, we take a slightly larger class, right? And you have to do this for different games separately, so let's look at Büchi games. What is a Büchi game? There are infinite games where one player wins if he can hit a good position infinitely often, some good position infinitely often, right? And this is, in a sense, the simplest class of games that are not just interesting, but really, really interesting in this setting, because they require, the formula that describes that this is a winning position requires an alternation between greatest and least fixed point. So it's not a least fixed point process to say this, right?
Erich, quick interruption. So maybe many people, maybe myself, we don't know what a Büchi game is. Is it with K pebbles? Or,
no, a Büchi game is a game played on a game graph, right? And the winning condition is not just that you have reached some good position, but you have to reach some good position infinitely often.
And how many pebbles are there?
Or you just move one through the graph. You move through the graph, right? The players construct an infinite path through the graph, and the first player wins if a good position is hit infinitely often, right? So it's, let's say, the step when you have reachability games and safety games, so the step immediately after is are Büchi games, right?
I mean, I see that a Bücherton has an acceptance condition that looks very much like this, but
that's the name.
Two players could reach a good position infinitely often.
No, see, so we just have I mean, it's a zero-sum game in the sense one player wants to reach a good position infinitely often, and the other player wants to avoid that. So the other player has what we call a co-Büchi condition.
But they could both reach their condition, their goal.
No. Every play reaches either a good position infinitely often, or just fine, or no, it reaches no position.
But it could switch between a good and a bad position infinitely often. Right?
It's not a problem.
So the other player that plays against the first player is not trying to get a bad position infinitely often.
No, he's trying to avoid that the good position is seen infinitely often. So the other player, I mean, you can look other games as well, right? But this is a game where one player has a Büchi and the other a co-Büchi, the same co-Büchi condition. So the appropriate strategies here are something that we call absorption dominant, which is slightly more general than the positional strategies. A positional strategy just means whenever you reach the same position again, you do the same move. Yeah? Here, you don't have to have this, but you minimize, in a sense, not the set of moves that you use, but the multi-set of moves. You cannot remove any occurrence of a move without losing the property that you win. Right? And now in this case, the sum of strategies theorem tells you that if we have such a Büchi game and such an interpretation into some absorptive, not fully continuous semiring, then, well, the valuation of the position is the same as the sum of the valuations of the absorption dominant winning strategies. You see the analogy to the result about proof trees, right? But it's now in the more general setting where your strategies are not just, say, finite proof trees, right? But you have strategies that work in some infinite games. But it's the same basic idea. And if we look at this not for Büchi games, but for acyclic reachability game, we get back the other result. So you ask what you can do. What is a strategy analysis? So here is what the strategy analysis tells you. So from this polynomial that describes, in a sense, all absorption dominant strategies, you can derive many things, right? The player 0 wins if and only if this polynomial is a non-zero polynomial. So then that is a winning position. You can get the edge profiles, that is, which edge are used and how often are they used for each of these absorption dominant strategies. And since you can easily, when you look at such a strategy, easily decide whether it is a positional strategy or not, you also get the number and shapes of all positional strategies. And you can answer other questions. You can answer the question whether a player can still win if some subsets of the move is forbidden, right? So these are taken away, right? Deutsche Bahn has taken away connections. Can you still reach your... probably you can't, right? But it tells it to you, right? You can also do repairs, right? So just very sketchy. So assume that the player loses from a position, right? Which will mean that your polynomial is 0. So the question is, what are the minimal modification of the game that make a player win? So which moves can you add or delete, right? And this can now determined by a semiring valuation in this dual indeterminate variant, right? Taking into account the sets that you are allowed to add or the moves that you are allowed to delete, right? And the polynomial keeps precisely track of the possibilities. So each monomial will tell you a possibility to repair your game so that you win. 10 minutes or? Yeah, okay. And this is not just limited to tracking edges. You can also consider other kinds of change in the game. So eventually it tracks a winning condition, right? So you look, how can we change the winning condition? So I set down this position, now becomes a good position. Can I win then, right? So of course, one has to develop this in more details, but in principle, it's possible to do repairs as it is possible to do repairs for database queries in the classical setting with respect to the two-term polynomial of the natural numbers, right? Of course, the question is about, can you compute these things really, right? Matthias will talk about possibilities of computation in algorithms in this setting of absorptive semirings. You can compute them. It's efficient with respect to the number of operations that you use compared to the size of the object that you compute. But the problem is that in general you have an exponential number of such strategies, and you have an exponential number of minimal repairs. So to make it practical, you have to limit the number of objects that you really want to track, right? If you have only small potential changes, then you can do it, but in general, you're solving here an exponential problem and you can't avoid this. Okay, so in the remaining little time, let me address the third thing. So to what extent do classical results of logic generalize to semiring semantics? So far we looked at 4 different such topics. One is elementary equivalence versus isomorphism. So when you have finite structure, then elementary equivalence and isomorphism are the same, because every finite structure can be axiomatized by a first order sentence. That is not true for infinite structures in general, but a finite structure you can precisely describe, right? A trivial fact, right? 0-1 laws. Every first order sentence is either almost surely true or almost foolish true on random structures, right? Famous 0-1 law by Graedel and Fagin from the 60s and 70s, right? Third thing, locality. Yeah? Theorems of Hamp and Geifmann tell you that first order logic can only express local properties, and in fact every first order formula is equivalent to what's called Geifmann normal form. Last thing, Ehrenfeucht-Froissart games provide a sound and complete method for establishing logical inequalities. Now, it turns out that all the definitions that we use in these observations, the definitions generalized to semiring semantics in a relatively straightforward way. Sometimes you have to pose some restriction, but this works. But what about the results? Right? This is not at all clear that the results survive for semirings. And for fact, for elementary equivalent versus isomorphism, they in general don't. They only do in some cases, right? So what is the situation, right? Both elementary equivalence and isomorphism generalize, right? So elementary equivalence means that every formula gets the same semiring value in both semiring interpretations, right? So what before was a property of two structures, now a property of two semiring interpretations, right? So elementary equivalence has its natural counterpart, and so does isomorphism. You have a bijection that preserves everything, right? So in Boolean semantics for finite structure, these are the same, but this fails in semiring semantics. In fact, there exist very simple semirings, namely a min-max semiring with 3 elements. Recall semiring, min-max semiring with 2 elements is just a Boolean semiring. So going one step beyond gives you a semiring where this no longer survives. And in fact, which is so finite semirings interpretations are not always first order definable up to isomorphism, right? This is because the formulae cannot really access the semiring value. So you, in general, it's not possible, or it's not always possible, to interpret such a semiring interpretation up to isomorphism. Sometimes you can, but if you can do it, you cannot infer that can do it with a finite set of axioms. Sometimes you require infinitely many axioms. And even weirder, even if you can do it finitely many axioms, you cannot necessarily do with a single sentence. Classically, if you have a finite axiomatization in logic, which takes the conjunction of the atoms, you have an axiomatization by a single sentence. This does not work here because you cannot get back necessarily the value of the conjunctions when you know the value of the conjunctions, right? So, but there are other semirings where it works. So the results here are a certain partial classification of the semiring where this holds and where this does not hold. 0-1 loss. Random structures also generalize to what we may call a random semiring interpretation, right? Just fix a probability distribution on the non-zero element of the semiring, that those that correspond to true. Then for each atom over a given universe, make a random choice, to toss a coin, whether the literal is true or its negation. We want model defining interpretations here. And then randomly assign a semiring value to the true literal according to the chosen probability distribution. Right? So this gives a notion of a random semiring interpretation. And the question is, does the 0-1 lot generalize? And it generalizes for many semirings in a quite interesting way. Right? Namely, with probabilities converging to 1 exponentially fast, the valuation of any given sentence almost surely concentrates on one specific semiring value. So this means really, as you have in classical logic a partition of first order logic into the sentences that are almost surely false and those that are almost surely true, you have here a partition into the sentences that almost surely evaluate to a particular semiring value j and j. But so the interesting thing is that this partition collapses. So for most of the semiring values, there are no sentences that evaluate these values. The only things that survive are the value 0, the value 1, and the smallest positive value. So if you have a min-max semiring, it's the smallest. If you have a lattice semiring, it is the infimum of the positive ones. Right? So you have every sentence almost surely evaluates just to one of these 3 values.
And Erich, when you say for many semirings, this means that you have identified particular semirings.
Yes.
For which it falls, or it's a class-defined axiomatic.
So, okay, I mean, I cheated here, of course, a bit. So, I mean, it definitely works for min-max semiring. It always works for lattice semiring, and it works in a different way for the natural semiring. Right? I mean, we'll have to state it differently, but there is, let's say, an analogous result that works also for the natural semiring. There are also results on absorptive semirings, but they're not quite this. So for many semirings, you can do the analysis. Of course, it requires new method. It requires that you describe formally by certain kind of polynomials or other algebraic expressions. So how much time do I have? Should I stop?
2 minutes.
Okay, so let me to say something about locality. So classically, there are two kinds of locality theorems in logic. There is Hanf's theorem, there is Greifmann's theorem. Hanf's theorem gives you a locality criterion for M equivalents of two structures based on the number of local substructures of a certain isomorphism type up to a certain threshold, right? So it's, I don't want to state it precisely, it just gives such a criterion for M equivalence that is indistinguishably up to quantifier rank A. As the Greifmann normal form theorem says that every first order formula is equivalent to a Boolean combination of local formula and in particular of sentence that express there exist 17 disjoint substructures of radius r with a certain property. Right? And in Semiring Semantics, we say that this theorem of Hanf generalizes, but it only generalizes to fully idempotent semirings. That is, semirings where both addition and multiplication are idempotent. Right? S plus S equals S, S times S equals S. Right? Once you have this condition, then the classical proof survives. But if you don't have it, it does not survive. More interesting is Greifmann's theorem. Right? Formulae with free variables do never have Greifmann normal forms if you don't have the Boolean semiring. For sentences, the Greifmann theorem also fails in certain semirings, such as the natural number and the tropical semiring. But, and this is the main positive result, we have Greifmann normal forms over min-max semirings and lattice semirings. Right? So, and in fact, we also have results on Ehrenfeucht-Freycinet games, but for reason of times I will not state this. So what all these analyses tell us is that, well, for certain semirings it works, and for other semirings it doesn't, depending on the question you ask. And the intuition is that, well, we have a certain hierarchy. When we go from the Boolean semiring to min-max semiring, many things work. When we go to lattice semirings, still many things work. When you go to absorptive semirings, fewer things work, but you still have a chance. When you go to the natural semiring, everything breaks down. Well, almost everything breaks down, right? And of course, there are many other, say, logical questions that you can ask. And particularly, you can ask, is there a reasonable proof theory for this, right? And I think the only chance where this may work is in absorptive semirings, right? Because you need the fact that multiplication is decreasing, right? But in a sense, we do not have this yet, right? But there are a number of such logical questions that we pursue. And the goal is to make Semiring Semantic really well, consistent and usable theory that works in many scenarios. Thank you.
Okay, so we don't have much time, but I think we should still take one or two questions from the audience. I do have a question. So, your premise is an asymmetry between falsehood, which can only be 0, and truth, which can have various degrees. What happens if you drop this asymmetry? If you allow multiple degrees of falsehood, not just 0, but other values of the semiring, and the same for true?
Well, I mean, this has been done for a long time in multi-valued logic. So multi-valued logic is, of course, just this approach. You have many truth values, right? You have different shades of truth, right? So you want to interpret things like possible and so on. So, for instance, in Lukasiewicz logic, right, you have all these, or in fuzzy logic, right, you have different degrees of truth. And there are many results about that, right? I think really it is important that the intuition here is different, right? I mean, the intuition here is not that the values are some shade of truth, but they are true that is annotated in some way, right? And if you want to annotate also falsehood, then I would do a different approach. Then I would proceed as following. I would interpret it, any formula, not by one semiring value, but by two semiring values. One for the formula itself and one for its negation, right? So to regain the symmetry, right? We have, let's say, come up with definitions for that, but we have not really done any serious work on that, right? But I think it's really important that that semiring provenance has a different intuition or different goal to start with than, let's say, many-valued logics as they have been pursued in many decades of logical studies.
Got it. Okay, I really think we should stop here and go for coffee.
A quick high-level question, which might not make sense. So semirings have had enormous success with these sort of languages like Datalog. Can you comment on any work for, say, a Turing-complete language, Prolog or Python?
We haven't really done any work.
Okay, so Erich will be around. We can talk to him over coffee. So let's thank him once again.